Alrighty, CNT120, we are looking at Chapter 5 on cabling. Here's our objectives. We're going to go over some terminologies and characteristics of transmissions, or transmission, some characteristics of copper cabling, characteristics of fiber cabling, and also some tools and troubleshooting tools and meters, if you will, for dealing with cable problems. Alright, first area we talk about some transmission basics. We need to remember early Ethernet network we use coax cable, modern Ethernet network we use twisted pair as well as fiber optic and even wireless. So as we transmit signals, if we're using copper cabling, it's going to be pulses of electricity or current, if you will. Pulse of electricity represent a 1, no pulse to represent a 0 type thing. When we deal with fiber optic cabling, it's pulses of light. A pulse of light represents 1, no pulse of light represents 0, if you will. And as we're dealing with any kind of wireless link, we're dealing with radio frequency. We're dealing with modulating that frequency, that radio frequency, to represent ones and zeros. So those are like basically three different ways that we transmit our signals: through copper cabling, fiber optic cabling, or radio frequency. We're mainly going to be focusing on the copper and fiber in this chapter. Chapter 6 we'll be looking at wireless or radio frequency. One of the first terms we run across is frequency. Frequency, they give you a definition here, basically measured in megahertz or gigahertz. The cable's maximum frequency is important to know because that affects basically how much data it can send. The faster that we can change a state from like no pulse of electricity to a pulse of electricity, the more times we can do that per second, the more data we can send across that cable. So that's kind of important to recognize, if you will. Bandwidth and throughput. Bandwidth is basically the capacity. What is the capacity of this link? But throughput is what we're actually getting. So think about a highway, 3-lane highway. We supposedly get so many cars through per time, but reality is, well, there's construction, so it's down to 2 lanes. We're not getting as much car through per time, so my throughput is down because of the construction, if you will. They use this picture in the book as a way to represent these, and it's actually a pretty good idea. The frequency that traffic light going on and off is, how many cars I can let through at a time and then stop, let through at a time and stop. That's the changing state, if you will. The bandwidth is how lanes of the highway, and again, no obstructions, what would be feasible, but the throughput is what's actually getting through, again, because maybe potholes or a lane is closed for construction, that sort of thing. The actual how many are getting through. And then they kind of remind us in the fine reading that if I use the same 3 lanes of traffic, the same green light frequency, you can transport dozens more people by using a larger vehicle like a bus or a series of buses. That gets us into the terms of modulation and encoding. Modulation is sending data over an analog signal. I'm modulating the frequency, frequency modulation or amplitude modulation. Whereas encoding is converting that into a digital signal for transmission, ones and zeros into bits, if you will. And with these techniques, I can send a lot more bits of data through on each change in state of that signal. So with using different modulation and encoding techniques, you can improve your theoretical throughput without necessarily changing the frequency or the bandwidth, if you will, getting more bits through per time. That's what we have a lot of these different technologies getting used to send data from A to B, using different modulations and different encodings to get more bits through per change in frequency state. They remind us about our prefixes, our bits per second prefixes. Don't forget your kilobit is 1,000 bits per second, your megabit is 1,000,000 bits per second, gigabit, billion bits per second, and your terabit is your trillion bits per second. Don't forget those metric prefixes, if you will. We also have some transmission flaws in the form of noise, and there's different types of noise. But noise in general is basically any undesirable signal. So I'm sending my data 101010, an outside source of interference was going to try to drown that data out. That is considered noise. That is measured, your signal strength as well as your your noise is measured in decibels. And decibels, it's a logarithmic scale, so it is not, when I go from 1 to 2, it isn't just up a little bit, it actually goes up like exponentially, if you will. So a general loss of 3 decibels, negative 3 decibels between transmitter and receiver indicates the signal has lost half of its power. And then that, again, I go another one and it's half of that, and then half of that. So it's going to decrease exponentially. It'll go so far and then like drop off significantly in its signal strength. Two common sources of noise are EMI and crosstalk. EMI is your electromagnetic interference. This is the interference from power lines, motors, machinery, photocopiers kicking off, air conditioners kicking on and off, fluorescent lights, power lines, those sorts of things. The electrical interference around them, there's magnetic fields around those lines and motors. Those magnetic fields induce or force in that signal onto the data wire, and it comes across as noise, and it can potentially drown out your data signal. So EMI is that. It's electromagnetic interference, interference from any of these things that they're mentioning here, pretty much anything that's using electricity. The other type of interference you can get is radio frequency interference. This is caused by strong broadcast signals from radio and television stations, the large antennas that are out there. That can potentially drown out data signals nearby on data lines, if you will. So here they're reminding of us EMI, power lines, lightning, those sorts of things, motors, that sort of thing is all forces of EMI. The other type is crosstalk. Crosstalk kind of has the terminology kind of comes back from the phone days. Once upon a time, as you had phone lines, you had literally copper wires that you were using to send your phone signal back and forth from you to the phone company and back. Well, every now and then you might have your phone line laying next to somebody else's phone line, and you would actually hear part of their call. So you can imagine that conversation cross-talking or jumping over to your wire. So that's kind of the roots of that term. But crosstalk is literally a signal from one wire or one wire pair jumping to a nearby wire. Again, anytime you send an electrical signal through a wire, it produces a low magnetic field. That low magnetic field can be picked up by a neighboring wire. And if that magnetic field is strong enough or that wire is close enough, that signal can literally induce itself or jump into that other wire. And that is called crosstalk. And there is different types of crosstalk: alien, near, and far. Alien is literally cable to cable, if you will. Actually, they're showing you a picture here of general crosstalk. Here would be near on crosstalk. I think I have alien here in a second for you. Near is literally a signal jumping from wire pair to wire pair near the source, whereas far in crosstalk is crosstalk measured out here to here. Signal here jumping to this out here. And then alien is literally from this wire pair, or I think they're showing you over here, a wire pair here, the blue wire pair here, to a neighboring blue wire pair here. That kind of deal. This is much harder to measure, but it can be an issue when you have large bundles of cables laying in cable trays. Another term they mentioned is attenuation, also called insertion loss. Insertion loss is a more up-to-date terminology. You'll see that on meters more so than attenuation. But attenuation is the weakening of a signal over a distance. So think about yelling across a football field or baseball field. If there's no game going on, there's no crowd there, when I yell across, you'll probably hear me just fine. But if I try to yell the same direction to you during the middle of a game, football game, baseball game, whatever, with all the crowd, you'll probably never hear me. It is weakening too much with all of the noise around me. So your attenuation is that signal loss over distance. And as long as there's not too much noise, some attenuation is fine. But if I have a signal loss with noise on top of it, I might not be able to, the signal on the other end might not be readable. Then that would be a problem. I can actually boost my signal, either old school amplifier or modern day repeater, if you will. Amplifier is kind of like an analog thing. Here is my signal and I'm getting noise. Well, the amplifier, as this signal weakens, the amplifier unfortunately boosts the original signal and the noise. Whereas in a digital signal, if I have noise interfering my digital signal, here's my pulses of electricity, pulse followed by none, pulse by none. That noise interfering here, when it hits a device like a switch or a repeater, it literally regenerates that 1010 as a clean 1010. And it basically just kind of filters out that noise. That your repeaters, things like switches and so forth, would do that. Latency, the term that denotes the delay. When I send a signal across a wire, it's not instantaneous. It does take a fraction of a second to go from one end of the cable to the other. Well, a long distance cable, that delay might be longer as it goes across the whole length of cable. So you can measure that in round trip time. In other words, how long it took for the packet to get there and a response to come back. That'd be the round trip time. And that would let you know something about the latency, or in some cases the length of that cable run based on that time. There are times when you are doing long distance transmissions that latency does matter. And I give you an example here of like a satellite. Commonly, when we have like the Olympics that are halfway around the world, whether it be Summer or Winter Olympics, reporters inevitably, you'll ask them, hey, how's the weather over there? And they look like they're standing there doing nothing, but that signal is still making it to them, and then they finally get the signal and respond back, oh, the weather's great over here, Frank. That is an example of latency. We all see it, we all kind of recognize it, we all kind of realize that, but at the same time we kind of forget it too. We forget that signal does actually take time to get there. And you can actually measure it. That is something that can be measurable. Now, if I do send data and there is some delay, we can have what's called jitter. When I have a series of packets arriving at the destination, maybe out of order or big breaks between them, that can actually cause errors. Think about sending voice over IP packets, my telephone call packets. When they arrive at the other end, if they arrive in order and just a little bit of delay, not a big deal. But if they start arriving out of order and big gaps in there, that can cause my phone call to be very choppy. They remind us of some terms about duplex, half duplex, simplex. Simplex, this would be, listening to radio. It literally broadcasts out and it's a one-way transmission. Okay, I basically can listen to the radio station. I can yell at my radio all I want, but they're not going to hear me. It is a one-way broadcast, if you will. Meanwhile, something that's half duplex would be something like two-way radios or walkie-talkies. When one person talks, the other one has to wait and listen. And then it flips around and so forth. This would be old school modems, that type of connection, and some early network connections were half duplex. While you sent, you waited until the response came back, if you will. Most modern network connections now are full duplex. I have some wires allocated for sending, other wire or wire pairs allocated for receiving, increasing your overall transmission speed. I threw a picture in here of a network card just to remind us that when I see this up here, this is auto-sensing the bandwidth connection that we're using, and my network card settings can be set to auto-negotiate. Once upon a time, you had to actually manually set this for the device you were connecting to. And as long as I got it right, no problem. If I got that bandwidth or the half or full duplex off, my communication to that device would not work because they were set differently. Most modern network cards, though, will auto-sense and set that for me, and I leave my network card on auto-negotiate. That's what we're seeing with that right there. This brings us to some terms called multiplexing. They did it real briefly in the book. I'm going to give you just a little bit more info. Multiplexing is combining a couple signals on one cable or one wire. Old school T1 lines would use time division multiplexing. So you'd have multiple phone calls, if you will, and it would take a little slice of each phone call in turn and send it across the wire together using little teeny time slots. Little chunk of yours, little chunk of yours, little chunk of yours, then would rotate back around. That was time division multiplexing, sending multiple phone calls across one wire using time slots. And an advancement that was statistical time division multiplexing. They would fill in the empty slots, if you will, with conversation. Meanwhile, frequency division multiplexing is using different frequency bands. This is how DSL worked. Your phone call was transmitted across one frequency band, and the data at your home using the DSL modem would modulate that into an upper frequency band up here to send the data in a higher frequency band. All right, we'll continue on the next podcast here.